Hello guys, and welcome to this channel once again. And of course, we'll be looking at buffer solutions. All right, so buffer solutions is a very crucial aspect of inorganic chemistry that cannot be ignored. All right, so it's a broad aspect of the study of acids and bases. Take note of that. But now, what then are buffer solutions? Buffer solutions are solutions that shows resistances to changes in pH whenever small amounts of acids or bases are added to it. So any solution that resists change in pH whenever you add small amount of acids or basis is called a buffer solution. So those are buffer solutions. All right. But then buffer solutions do not always remain buffer solutions. There is what we call buffer capacity. Buffer capacity. So buffer capacity can be defined as the extent to which a buffer solution do not resist changes in pH. Do not resist changes in pH whenever acids and bases are added. So it's more like the extent to which you would add acids and bases that it will no longer resist, or the amount of acids and bases that you would add that will no longer enable the buffer solution to resist changes in pH. All right. So basically, when we look at buffer solutions, we have different types of buffer solutions. As a matter of fact, we have two major categories of buffer solutions. All right, the first one is what we call the acid buffer, and the second one is what we call the base buffer. All right, so an acid buffer is actually a buffer solution that contains a weak acid and its conjugate base. A weak acid and its conjugate base. While a base buffer contains a weak base and its conjugate acid. So one thing you must take note of is this. Just weak acids and bases act as buffers. All right. So if we have a weak acid and its conjugate base, an acid buffer is formed. If we have a weak base and its conjugate acid, a base buffer is formed. Very simple. Now, another thing we must understand is that when we look at conjugate base and conjugate acid, both of them are salts. All right. So most times you would see in place of a conjugate base, salt is being used, and in place of a conjugate acid, salt is being used as well, which implies that both of them act as salts. Both of them act as salts, but for weak acid, it must be conjugate base. It's not weak acid and conjugate acid. It's weak acid and conjugate base. It's not weak base and conjugate base. It's weak base and conjugate acid. Very, very important to note. All right. So now there is a theory that actually helps us to understand the behavior of buffer solutions. All right. And of course, that theory led to an equation which is called the Henderson-Hasselbalch equation. All right, and that's in Hasselbalch equation. Remember the theories of acids and bases. We have the Arrhenius theory, we have the Anderson-Hasselbalch theory, okay, and of course we have the Lewis theory. So the Anderson-Hasselbalch theory is what bettered, is what led to the Anderson-Hasselbalch equation. Very, very important to note. Okay, so now before we look at the Anderson-Hasselbalch equation, we'll look at examples of buffer solutions. So for acid buffer, we have different examples. We have the major example of an acid buffer. It is called the acetic acid buffer. Acetic acid buffer. All right. Acetic acid buffer is actually one example of the acid buffer. So an acetic acid is of course also known as ethanoic acid. And acetic acid is given as CH3COOH. So when acetic acid reacts with what we call ethanoate, sodium ethanoate or sodium acetate, all right, which is CH3COONA, then an acetic acid buffer is formed. All right, so acetic acid plus sodium ethanoate is also known as sodium acetate. When these two react, we form an acetic acid buffer, and it has what we call Ka. Ka is called acid dissociation constant. So the value for the acid dissociation constant of the acetic acid buffer is equal to 1.8 times 10 raised to power minus 5. All right, 1.8 times 10 raised to power minus 5. It has no units. All right, so Ka does not have units. So Ka is acid dissociation constant. We also have Kb. Kb is base dissociation constant. One thing we must know is that the potential of your acid dissociation constant is known as your pKa, and pKa is minus log Ka. All right, negative logarithm of your acid dissociation constant. All right, so now let us look at another example. Another example of the acid buffer, all right, is what we call the formic acid buffer. All right, formic acid buffer. So formic acid buffer contains formic acid plus sodium formate. Sodium formate. Formic acid is represented as HCOOH. All right. So sodium formate is HCOONA. All right. So this sodium formate, this formic acid. All right. They have a dissociation constant of 1.8 times 10 raised to power minus 4. All right, this one is minus 5, this one is minus 4. I want you to understand that these values tends to be constant for these buffers. All right, other examples of acid buffers are, of course, we have the phosphate buffer, we have the carbonate buffer. All right, then for base buffers are, of course, buffer solutions that contains weak bases and their conjugate acids. Weak bases and their conjugate acid. Very, very important to note. All right. So one very crucial example of a base buffer is the ammonia. Is the ammonia base buffer. All right. So you know ammonia is a weak base. So when ammonia reacts with ammonium chloride, when ammonia reacts with ammonium chloride, ammonia buffer is formed. Now ammonia is NH3. So NH3 plus NH4Cl gives you the ammonia buffer, and it's a base buffer, and it has a Kb. This time around, we'll call it Kb. Kb is equals to 1.8 times 10 raised to power minus 5. All right. So the base dissociation constant for ammonia buffer is the same as the acid dissociation constant for, of course, acetic acid. So let's look at the examples. All right. But before looking at the examples, let us like state the Anderson-Hasselbalch equation for buffer solutions. All right. So quickly, let's do that. Now, for your acid buffer, the acid buffer has its own formula, while the base buffer has its own formula. For your acid buffer, to get the pH, because the most important thing we need to know is the pH of the buffer. Since we are saying that the buffer solution is not resisting any change in pH, it means that it has a constant pH. So for that particular solution with given concentrations, it's important to know the actual pH. All right. So the pH of an acid buffer is gotten by pKa plus log conjugate base all over acid, all over weak acid. All right. Conjugate base all over weak acid. Now it's important to note that this conjugate base is salt. So sometimes you can see it written like this: salt over acid. It's still the same thing. All right. Then for the base dissociation and of course the base buffer, pH now will be equals to pKb plus log conjugate acid divided by weak base. And of course, this is also salt over base. So it's very, very important to note that. All right. So these are, of course, the formulas for your acid buffer and your base buffer. All right. So we'll be looking at examples. Let's delve into example. Let's take the first one. Determine the pH of an acetic acid buffer which has a concentration of acetic acid giving us 5 times 10 raised to power minus 6 mole per dm cube, 5.6 times 5 times 10 raised to power minus 6 mole per dm cube, and the concentration of the sodium ethanoate to be 1.5 times 10 raised to power minus 6 mole per dm cube. All right, then in bracket, you say Ka equals to 1.8 times 10 raised to power minus 5. All right, so one thing you need to understand is that they will give you Ka will be given to you in the question. All right, so now let us solve this particular exercise as quick and as fast as possible. All right, so the first thing we have to do is to state our parameters. All right, so that's the first thing we must do, state our parameter. So of course, we are giving parameters, we are giving the concentration of acetic acid CH3COOH to be equal to 5 times 10 raised to power minus 6 mole per dm cube. Now, mole per dm cube can be represented as capital letter M, which is molar, or mole per liter. Very important to note. All right, so that is the concentration of the what? Of the acetic acid. Now, for your sodium ethanoate, it is CH3COO Na. All right. So the value for this given in the question is 1.5 times 10 raised to power minus 6 mole per dm cube. Now it's very important to know these three places. All right. So it's very important to note that when it comes to pH, all right, when it comes to pH, normally in pH it is negative logarithm of hydrogen ion concentration, but here it's not normal pH we are looking at. We are not looking at the pH of a normal concentration. We are looking at the pH of a buffer solution. That's why we must use the Anderson-Hasselbalch equation. All right, so now look at these guys. So now stating our formula, pH is equals to pKa. We are using this formula because a this is a buffer solution that contains an acid buffer. So we must use the acid buffer formula. So pKa plus log salt over acid. Remember, I told you that the main acid is the weak acid, while the main base is called the conjugate base. Okay, the not main base, rather the salt is called the conjugate base. All right. So, like I said, at the top here, this thing is the same thing as saying um, concentration of conjugate base all over weak acid is the same thing. They're used interchangeably. All right, so these and these are the same. All right, so let us just plug in our formulas. So our pH now will be equal to pKa is minus log Ka. That's the formula for pKa. I gave it to you. And the pKa is minus log Ka plus log your salt is your conjugate base, and your salt is sodium ethanoate, while your weak acid is, of course, acetic acid, which is ethanoic acid. All right. So now, quickly, we'll have to plug in or substitute the values. All right. We substitute the values into this exercise. And of course, we have pH now will be equals to minus log your Ka that was given to you, which is the standard Ka for acetic acid, is 1.8 times 10 raised to power minus 5 plus log your sodium the sodium ethanoate has a concentration which is given as 1.5 times 10 raised to power minus 6, all divided by the concentration of the acetic acid given is 5 times 10 raised to power minus 6, close the bracket. So it means that your pH is this. So we have to first of all check what the pKa is, all right? So get your calculators. So we'll now check. We see minus log, all right? Minus log of bracket open 1.8 times 10 raised to power minus 5. All right. So this is about, okay. So that is 4.7447. All right. So this is, of course, the negative logarithm of your Ka. Now plus log. Now you divide. Okay. So now let's quickly divide 1.5 times 10 raised to power minus 6 by 5 times 10 raised to power minus 6. So this will give us 0.3. All right, so now we have 4.7447 plus log 0.3. So when we get the log of 0.3, okay, when we get the log of 0.3, that will give us minus 0.522. So we'll say minus 0.522, or let's just say 23 approximately. So this will be 4.7447 plus times minus is minus 0.523. Okay, so this would be 4.7447. Okay, 4.7447 minus 0.523. All right, so it means that we'll have 4.2217, approximately just 4.2 as the pH. All right, so this is the answer. So our answer here is 4.2. So that's the pH of this particular buffer solution given to us. All right, so quickly, let's look at another example. Okay, let's look at another example relating to a base buffer. All right, relating to a base buffer. So now please take down, determine the pH of a base buffer containing molar concentrations of 2.5 times 10 raised to power minus 4 and 1.8 times 10 raised to power minus 4 for ammonia and ammonium chloride respectively. So 2.5 and 1.8. So we have 2.5 times 10 raised to power minus 4 mole per dm cube and 1.8 times 10 raised to power minus 4 mole per dm cube respectively for ammonia, and ammonium chloride. So now you put in bracket, you say Ka is equals to 1 point, in bracket you say Ka equals to 1.8 times 10 raised to power minus 5. All right, so that is, okay, here is Kb, all right? So Kb, okay, please, Kb. Because this is a base buffer, so of course, this is supposed to be a base dissociation constant, not an acid dissociation constant, all right? So now let us provide solution to this exercise. Now look at this, guys. Now solution to this, simple. We are looking for the pH of a base buffer. So we'll state our formula. So pH will be equals to pKa, pKb in this case, plus log salt all over base. All right, log salt over base. This salt is the conjugate acid. Please don't forget. A weak base has a conjugate acid, while a weak acid has a conjugate base. All right, so it means that the pH here will be negative logarithm of your Kb, that is your base dissociation constant, plus log of your salt. In this case is ammonium chloride, which is NH4Cl. This will be in square brackets. All right, it's in square brackets because we are dealing with concentrations. All right, so that's why it has to be in square brackets, divided by ammonia itself. Ammonia is the weak base, while this is the salt or the conjugate acid. All right, so now it means that your pH will be minus log, your Kb is 1.8 times 10 raised to power minus 5 plus log the concentration of your conjugate acid, which is of course the salt here, is given to us. Remember this, the question stated this and this respectively, which means that it's the second one that is for NH4Cl, which is 1.8 times 10 raised to power minus 4, while the first one is for your ammonia, which is 2.5 times 10 raised to power minus 4. All right, so it's important to take note of that. Now, so we have to take it step by step. Of course, we have already done a similar thing like this because pH is now equal to, this was the same dissociation constant we use for our acid buffer. All right, so we had 4.7447 when we calculated it. Now we say plus log of, now we'll now have to divide, in this case. Now we'll say 1.8 times 10 raised to power minus 4, all divided by 2.5 times 10 raised to power minus 4. So when we do this division, we'll be having 0.72. So this will be 0.72. All right, so this will be equals to 4.7447 plus, let's do our log, the log of 0.72. So this will give us, put in bracket, minus 0.1427. All right, so minus 0.1427. So removing that bracket, we have 4.7447 minus 0.1427, because plus times minus is minus. So we say 4.7447 minus 0.1427. So this will give us 4.602 as our pH. So this is the pH of the what? Of the base buffer containing ammonia and ammonium chloride. All right, so very important. Now we'll be looking at one last example. This last example will be for us to determine the concentration of a particular conjugate acid or base or a weak acid or base. All right, so I'll give you the question, then we'll know what we are looking for in this case. All right, so please take down. Now, given that the concentration of a formic acid sample is 1.69 times 10 raised to power minus 4 mole per dm cube, 1.69 times 10 raised to power minus 4 mole per dm cube. Determine the concentration of its conjugate base, So in bracket, you say Ka equal to 1.8 times 10 raised to power minus 4. Close the bracket. Okay, close the bracket, comma, given that the pH of the buffer solution is 6.18. All right, given that the pH of the buffer solution is 6.18. So now if you look at this, you will realize that you are giving the concentration of formic acid. You're also giving the acid dissociation constant and you're giving pH. So it is now evident that in this question now pH is known, but one of the concentrations are unknown. I want you to understand that both cannot be unknown. It's either you have pH and you don't have the concentration of one of the samples, or you have one concentration of the sample and you don't have pH. So it's very important to note that. All right. So now at this point, we'll be solving this. So as our custom has always been, we would have to first of all state our parameters. All right. And stating our parameters now will guide us into providing the accurate answer for this exercise. All right. So quickly, the parameters that we are giving, of course, are HCOOH, which is formic acid, and formic acid, we are giving a concentration of 1.69 times 10 raised to power minus 4 molar. Molar, mole per dmq, and mole per liter are used interchangeably. They also have HCOONA, which is called formate or sodium formate, with the concentration is unknown. Then we have Ka to be 1.8 times 10 raised to power minus 4. This is Ka. Then, of course, then we have the pH to be 6.18. All right, so the pH is 6.18. All right, so now quickly, knowing that we have parameters like this, all right, so we'll quickly go straight into solving this exercise. So this is an acid buffer, and an acid buffer, as we all know, is pH equal to pKa plus log salt all over acid. Remember, this acid is the weak acid. All right, and the weak acid here is formic acid. The weak acid here is formic acid. Okay, all right. So now quickly, we'll be solving this. Now, pH is given. pH is 6.18. All right, your pKa now will be minus log of your Ka, 1.8 times 10 raised to power minus 4, minus log. The salt here is unknown. All right, so we say salt divided by formic acid has the concentration 1.69 times 10 raised to power minus 4. Now, it's very important for us to, first of all, determine the negative logarithm here. All right. So the negative logarithm here is the first thing we'll determine. All right. So now, if if we have negative logarithm of, so we have minus log of course 1.8 times, okay, times 10 raised to the power of minus 4. Okay, so this will give us 3.745. So we see 6.18 equals to 3.745 minus log. Now the salt here is still unknown, of course. divided by 1.69 times 10 raised to power minus 4. All right. So, okay. So at this point, we have to make salt subject to a formula. We have to make salt subject to a formula, but we have to move this first. So this will be 6.18 minus 3.745 equal to minus log of the salt all divided by 1.69 times 10 raised to power minus 4. All right, let us subtract 3.745 first of all from 6.18. So we say 6.18 6.18 minus 3.745. So when we do that, we'll have 2.435. This one will now be equals to minus log of our salt divided by 1.69 times 10 raised to power minus 4. All right, you can see this. Remember, all these are in brackets. They are all in brackets. So we cannot remove 1.69 times 10 raised to power minus 4 like that. We have to first of all remove this guy by taking the antilog of both sides. So we'll say antilog, take antilog of both sides. So when we take antilog of both sides, the antilog of both sides now will eliminate this negative logarithm. All right, we eliminate this negative logarithm. All right, so at this point, now we would now have to take the antilog of both sides. All right, so now we will now have, okay, we'll now have antilog of 2.435. All right, so it will now be, okay, shift log then 2.435. So we'll have 272.27. So this will be like 10 raised to power, 10 raised to power this will give us 272.27. There's no need writing 10 raised to power because we have already gotten this as an answer. Then of course we will now have antilog, will remove that. So now we'll now have um, the salt all over 1.69 times 10 raised to power minus 4. At this point, we don't really need to do any form of anti-log again and all of that. We just have to cross multiply. So we have 2.72 or 272 rather 0.27 times 1.69 times 10 raised to power minus 4 equal to the concentration of the salt. So now we'll multiply that our answer. We say we had 272.27. All right, so when we multiply it by 1.69 times 10 raised to power minus 4, okay, this will now give us 0.046. Okay, 0.046. That will be equal to the salt. Remember that the salt here is your formic formic conjugate base, which is your sodium formate. All right, so and which is HCOONE, of course, is 0.046. But mind you, this is plus, all right? Mind you, this is plus from here. So it's positive from here. Okay, remember, this sign is never supposed to be here because, of course, we know that our pH is equals to pKa plus log salt all over acid. When this guy moved, we'll be left with log salt over acid. So we have to take the antilog of both sides. This one eliminated. We took the antilog of when we subtracted this from this, and we cross multiplied to get the concentration of our salt. All right. So that is that for buffer solutions.